Right, so Assalamu alaikum everyone. Apologies for starting up late. Any questions before we start? Okay, just to briefly recap, in the last lecture we talked about, first of all, what did we talk about last time? Anybody? Kuch yaad hai? We talked about classful, class and site addressing. Then we talked about natting as a hack to sort of work with the limited IPv4 space that one has using private networks. And then we talked about the problems one has when trying to connect directly from outside a firewall to a host which is connected behind a NAT. Then we talked about ICMP as well as IPv6. Okay. IPv6 के बारे में we were talking, and IPv6 में the challenge, of course, is the transition from IPv4 to IPv6. IPv6 is the newer version of IPv4, and you might ask, the IPv5 kahan gaya? So IPv5, the idea was that ST2 is going to become IPv5. That was another protocol, but that faded out. So we never had IPv5 or ST2, and IPv6 is the next version. 1996 mein, way back, it was finalized, and पिछले 24 साल से it is still in transition. You can check up on the APNIC site के Asia Pacific में, for example, कितने nodes up IPv6 compliant हो गए हैं. So IPv6 and IPv4 typically work on newer routers, and उसमें ये है कि both the algorithms work, which means that the routers are dual stacked. The header of IPv6 is इसका जो format है, it's a 40-byte header, and once again the first few bits define the version. Then of course you have bits which specify the priority of a particular packet, and then a flow label. And we said the flow is a concept that designers might want to use, and the flow could be associated, for example, with a particular voice channel, or it could be associated with a particular video stream, and so on, so that जो packets आ रहे हैं, the router can somehow identify that किस flow को ये belong करते हैं, and उसके मुताबिक जो है ना treatment की जा सके potentially. Then you've got the payload length, which is 16 bits, so 65,535 bytes तक के आपके पास payload possible है. The next header specifies that what is the protocol that is being carried in the payload, and then once again TTL की तरह आपके पास hop limit वाला counter है यहाँ पे. And then you have a simple 128-bit source address and a 128-bit destination address. So it's a very simple header, which results in very fast processing, and it's very, very efficient. Now, the challenges, of course, then are, why don't we actually use it? And the reason is legacy. You've got hundreds of thousands of IPv4 routers in place, and un sabko transition karna is not an easy task. And so because that's not an easy task, so at the moment, you've got to interoperate between IPv4 and IPv6 routers. And interoperation, the easiest thing that can happen is called tunneling. Now, just as the name suggests, tunnel, the idea is that you've got, for example, these routers A, B, C, all the way up to F. A, B, and EF are IPv6 compliant. C, D are IPv4 routers. So अगर आपने A से F एक पैकेट लेके जाना है, ठीक है? So you can view this that between B and E, ठीक है? ये जो बीच में routers हैं C and D वो IPv4 है. So you can think of that as an IPv4 tunnel that is going to connect these IPv6 routers B and E. So when you have a packet that's flowing, So you have a flow which is labeled as X, source A है, destination F है. So A to B IPv6 packet गया. अब चूंकि C जो है, the destination जो है from B to C is hop के ऊपर, that is an IPv4 router, which means that that router B cannot forward an IPv6 packet to C because C doesn't understand IPv6. So what B will do is that it's going to take the IPv6 packet and encapsulate that into an IPv4 packet. So remember, B can operate IPv6, but it definitely can also operate IPv4. So the B router here, that's dual stacked, and it's going to then take that packet, जो IPv6 वाला है, जो A से B तक उसको मिला है, and it's going to put that, encapsulate that into an IPv4 packet, which means that now this entire IPv6 packet, including the IPv6 header, becomes a payload for an IPv4 datagram that is forwarded from B to C. C, of course, when it reads this header, जो कि IPv4 है, उसको समझ आएगी इसके साथ क्या करना है, वो उसको next hop पे forward कर देगा, and इसी तरह से वो होते होते E तक आ जाएगा. Now, once it gets to E, because a tunnel has been prior established between B and E, so E knows कि अच्छा जी जो पैकेट B से आया है उसका हेडर स्ट्रिप करना है and बीच में से IPv6 का पैकेट निकल आएगा and उसको फॉरवर्ड कर देना है to the next hop. ठीक है? So by establishing this tunnel, an IPv4 tunnel between B and E, it is possible to encapsulate IPv6 packets and tunnel them between B and E effectively, and that is how you have this interoperation working. Any questions here? इसमें कोई चीज समझ आई? Any questions here? Okay, so we talked about adoption. It's been 20 years plus and counting, and the reason, of course, is that we don't have any flag days. As any possible that on one fine day we decide that everyone transitions. There are too many routers जो कि IPv4 को currently operate कर रहे हैं, and ना सिर्फ routers हैं बल्कि आपको सारे के सारे nodes को IPv6 addresses भी देने हैं, and which is a humongous task. And slowly, regional operators through their regional registries are registering more and more IPv6 addresses and training people, training different ISPs, training different regional entities so that they can slowly configure their routers, give new IPv6 addresses, and have a greater and greater share of IPv6 down the road. Now this brings us to routing algorithms, and routing algorithms are the protocols that routers run. So routers share information, and that information helps you build the routing tables, the forwarding tables, and we'll talk about these in some detail. Any questions? Okay, so we've talked about the interplay between routing and forwarding, and we've said that the routing algorithm is the protocol or the algorithm that runs between routers. So routers exchange information, and us information ki bina pe basically you set up an end-to-end path or end-to-end paths for possible destinations, all possible destinations, and uske zariye se then you create a local forwarding table. And the local forwarding table determines the next hop that is particular datagram ko aapko kis interface ke upar output karna hai. So you have a destination address, and to get to that destination address, you come up with the output link at this local router, so which is going to be the next hop interface that you're going to go on to, and that will ultimately get you to this destination address. So the question is, ये forwarding table actually construct कैसे होगा? How will this get constructing? And that is through a routing algorithm. And the routing algorithm has to determine the end-to-end path based upon a certain criteria, and then choose the best path, okay? And based upon that best path, figure out what should be the next hop or the output link जिसके ऊपर इस particular packet को forward करना है. So you can view this as with the graph abstraction, and graph, as you know, is a collection of nodes and edges. So for example, आपके पास ये routers हैं. You've got routers over here as U, V, W, X, Y, and Z. So these are a set of routers, and you can think of them as your nodes. Then you've got a set of links over here which connect these routers. So think of them as edges. Okay? So you have this edge U to V. This ऊपर we have a cost function over here, or a metric over here, which is 2. You have this link over here, which is U to X. इसके ऊपर एक value लिखी हुई है हमने 1. You have one from U to W, which is a metric over here, which is 5, and so on. So each of these edges, okay, which interconnects two nodes, has an associated cost metric over here, and we'll come to this in a minute. कि cost metric क्या चीज है? But now you can think of this network as a graph consisting of nodes and edges. So you can think of this as a set of nodes and a set of edges, which each of these edges maps to your links, and associated with each edge is a cost metric. Now, these costs of a link, so for example, you can think of this as a cost from X to X prime. For example, from W to Z, this link over here has a cost of 5. And this cost could be anything appropriate. So for example, if you set all the costs of every one of these links to 1, so that could represent कि कितने hops आप दूर जा रहे हैं. So that would mean 1 hop. From here to here, it's 1 hop. If it's directly connected, it's 1 hop. From U to W through V, you'll get there in 2 hops. So अगर हर एक cost को 1 set कर दें, so then as you take a hop, okay, and you sum up the total cost of a certain path, that's going to be the cost of each one of these links along the way, along the path. So जो भी links along the path आते हैं, you can simply sum up their costs. Now, how should one set the costs? Now, you could do it in one of 2 ways, but the usual convention is that the best path is the least cost path. So उसमें जितनी अच्छी path होगी, उतनी उसकी cost आप कम रखेंगे. So that would mean that you would want to have the cost inversely related to the bandwidth or the capacity of the link. So the greater the capacity, the lower the cost, and that would sort of favor paths which have a higher capacity. Okay? Similarly, it could be inversely related to congestion. So the paths which have higher congestion would have a higher cost. Those with lower congestion would have a lower cost. So that would favor paths which with a lower cost, as meaning with lower congestion. So the lower the congestion, the lower the cost. So inversely related to congestion is a metric that you could use. इसके अलावा you can have other metrics which are related to the actual physical price that you have to pay while using those costs. For example, if they belong to different ISPs and so on. But usually these algorithms work for within an autonomous system, within an AS, which belongs to the same ISP, the same entity controls that. So ये जो costs हैं, they are assigned in some uniform way. So you can think about this, कि अगर these routers were owned by different autonomous systems, then unless they agree upon that, how are they going to actually allocate these costs? It's going to become difficult to actually come up with this graph abstraction. So typically these routing algorithms are going to be used within a certain autonomous system. Okay? So the question over here is that cost could always be 1. अगर आप 1 cost आप रख रहे हैं, so then of course that is going to correspond to a hop. Okay? So then of course you would want to minimize the number of hops that you want to get from source to destination. Okay? And so the minimum cost is going to be 1. Once it come up, typically आप यानी इसको नहीं रखेंगे. If the meaning, of course, for the cost metric is going to be that it's one hop away. ठीक है? But of course, I mean, if you were using some other metric, you were not using hop count, you were using something related to congestion or something related to capacity. There is no reason why you could not have a cost less than one. आप कर सकते हैं. It's just going to be that उसका meaning different होगा. ठीक है? And in that case, once again, you would want to minimize the least cost from source to destination, and that could be anything, right? So it could be fractional. लेकिन basically for reasons of ease of calculation and whatever, rather than using fractional values, you simply use numbers. ठीक है? And that's why अगर आप hop count इस्तेमाल करते हैं तो हर hop को आप 1 कर सकते हैं. ठीक है? इसे cost directly proportional to congestions. उसका मतलब ये कि जितनी congestion ज्यादा होगी उतनी आपके पास cost ज्यादा होगी. Yeah, so that you're correct over here. ठीक है? So let's just correct that over here. एक second. Yeah. Oops. ये कहाँ से आ गया? और it should be, yeah, directly, not inversely. Thank you very much, ma'am. That's very good. So the greater the congestion, the greater the cost, and you are trying to minimize the cost. So then the question becomes, what is the least cost path between, let's say, U and Z? And the routing algorithm is going to find out all possible paths from U to Z and figure out what is the least possible path, least possible cost path. So maybe 1 and 1 and 2, right? 4 seems to be, because baki to 4 and 6 zyada ho jayenge, right? So yeah, U to X, X to Y, and Y to Z agar ye figure out kar le, so that would be great. Now the interesting thing over here is that yahan pe sitting up over here, you have a bird's eye view of the entire network. You can see all the links, you can see the nodes, you can see each one of these costs, and you can take a paper and pencil and figure this out for yourself. ठीक है? लेकिन मसला ये है कि in a network where you've got these routers, ठीक है, and they're connected to one another, these routers have to figure out for themselves, without having that centralized view, without having that bird's eye view, कि जी, okay, what is the least cost from U to Z? इन्होंने खुद figure out करना है, and वो कैसे करते हैं? That is through running a routing protocol, a routing algorithm. ठीक है? Now, you can classify these routing algorithms as centralized or decentralized. ठीक है? Global है या decentralized है. ठीक है? Global would be centralized. So global में all routers have a complete topology. They know the exact topology. They know कौन से आपके पास nodes हैं, edges क्या हैं, link costs क्या हैं. And if they have that complete topology and link cost information, a centralized kind of algorithm would be a link state algorithm. ठीक है? दूसरा तरीका ये decentralized है. So the router knows of its physically connected neighbors, so it knows its link cost to its neighbors, and through an iterative process, कि ये जो link cost to its neighbors है, इसको it exchanges this information with its neighbors, and through that you construct a routing algorithm. So ये जो cost है, इस cost को आप distance भी कहते हैं, ठीक है? And the path you take is a vector. So the distance vector algorithm is a decentralized method in which the nodes have this information, the link cost to their neighbors, and by exchanging this information with their neighbors, they actually figure out कि अच्छा, अगर ultimate destinations ये हैं, तो how can we get to the ultimate destination at a least cost? And इसी तरह से आप उनको classify कर सकते हैं as static, that routes change slowly over time, or dynamic, where routes change more quickly over time, in which you have to periodically update this information. So this information between routers is typically exchanged in the order of 30 seconds, maybe a minute, maybe longer, okay, depending upon how frequently routes are expected to go down. Ya phir they could be triggered on certain events, that if a certain event takes place, then that should be triggered. Now the question is, how would they know the event has taken place? So typically a router baitha hai, it's connected to another router, and they exchange some heartbeat information. They basically they keep checking up, Acha, is my neighbor still alive or not? And so they send a message to it, they get a response back, they know that Acha, my neighbor is up. It could be a TCP connection to the neighbor. And as soon as they send a packet and aage se acknowledgement wapas nahi aa rahi hai, then they, if that doesn't happen for a certain amount of time, maybe 3 tries or whatever, they know acha ye potentially neighbor down hai, and then they would take action to actually update their routing tables. Right, so any questions over here? Broadly speaking, दो classes हैं, एक link state algorithms है, which are centralized or global, or एक distance vector algorithms which are decentralized. Now we'll come to the link state ones first. The link state ones, a key example of this is Dijkstra's algorithm, and I believe you've covered Dijkstra's algorithm in your algos course. Lekin broadly speaking, very quickly, the net topology or the link costs are known to all nodes. And this is accomplished via a link state broadcast. And all nodes have the same information. So you're computing the least cost path from one node, the source, to all other nodes. So basically, आप एक tree बना रहे हैं where you are the sort of the root of that tree. So every node calculates कि अच्छा अगर मैं root हूँ, so all other nodes within the graph, what is the distance, what is the cost, okay? And I would want to find out the least cost to all other nodes using yourself as the root of the tree. So basically, this link state algorithms provide a forwarding table for that particular node. अच्छा मेरे पास packet आ गया है, अब I need to get to any of the destinations in the entire network, ठीक है? So what is the least cost from me to any of the particular destinations? That is the tree that is worked out, and then for that tree basically उससे फिर आप एक forwarding table बनाते हैं कि अच्छा मुझे अगर उस ultimate destination पे जाना है, least cost इतनी है, and वो through next hop किस node के through मुझे इस packet को forward करना होगा. So that's the next step. The forwarding table is the next step. But in order to make up that forwarding table, okay, you're going to have that information that what is the least cost distance from you as the source to all other nodes in the entire network. Now, this is an iterative process, okay? And this may basically will use a notation. And the notation, of course, is the cost from node X to node Y. Okay? So that's the link cost from node X to Y. So initially, you will know the cost to your directly connected neighbors. And जो आपके पास nodes are not directly connected to you, you will assume that the cost to them is infinity. Okay? So initially, you will only know the cost to your immediate neighbors, and the rest of the nodes in the entire network, unki cost आप infinity assume करेंगे. So unless you know better, the cost to the other nodes in the network which are not directly connected to you is infinity. Okay? You've got the D, which is the current value of the cost of the path from source to destination V. So brackets may notice you have the destination, which is V. So notice कि सारा काम आप एक particular node को hinge करके एक particular node को करके कर रहे हैं, तो उसी से आप सारी costs निकाल रहे हैं, अपने से ही आप सारी costs निकाल रहे हैं to all potential other nodes in the entire network. So to a given node V, what is the current value of the cost, इसको आप D कह रहे हैं, and D of course is the distance, ठीक है, इसी वजह से इनको हम यहाँ पे so we're using D over here, which is the cost or the distance to all the other nodes. Then you've got this P of V, and this is a predecessor node along the path from source to V. ठीक है, so ये एक node है. So P of V results in a node कि अगर आपने V तक जाना है तो V तक पहुंचने के लिए, node V तक पहुंचने के लिए उससे पहला जो node है वो कौन सा node है. So P of V is a node. It's a predecessor node to get from your source, from yourself to V. Along the way जब आप जा रहे होंगे तो V से एक पहले जो node है वो क्या है? That is P of V. ठीक है, and ये iteratively आप solve करेंगे इस network को. अब तक जितने nodes solve हो चुके हैं, ठीक है, उनको that set of nodes whose least cost is definitely known is n prime. ठीक है, so think of it as a bucket algorithm. Initially this bucket खाली है, या you can think of it you only know the cost to yourself, so you're the only node in that bucket, and as you find out definitely the least costs to other nodes within the network, आप उन nodes को bucket में डालते जाते हैं. So n prime grows. ठीक है, so just very quickly, C is the cost, D is the current value of the least cost to a particular node, P of V is उस node तक जाने के लिए उससे पहला कौन सा node होगा, and n prime is basically the set of nodes whose least cost is definitely known. ठीक है, so we'll come to this कि ये how does this work in a minute. You'll see this algorithm in action, but initially आप ये समझ लें कि आपने bucket में ये आप node U से शुरू करें, which is yourself. So इस bucket में n prime में आपने सिर्फ you've put yourself there, and then for all other nodes V, ठीक है, अगर तो वो node आपके साथ directly connected है, it's adjacent to you, the cost to V is the cost from U to V, you know that. Whereas all the other nodes which are not directly connected to you, उनकी cost आपने infinite कर दी. Then you simply loop, and while looping you try to find out कि अच्छा जी उधर तक जाने के लिए minimum cost है क्या है, and that is obtained by the exchange of information. And basically minimum जो cost है to a certain node V, वो निकालने के लिए आप कैसे करेंगे कि अच्छा जी उस node से जो है उसका जो predecessor है वहां तक आपको cost पता है, अगर पता है तो उसमें you will add the cost of that link, and that is going to be the cost to there. And ये जितने भी costs आएंगे आपके पास, you will choose the minimum one, and that's how you will be able to find out the least cost. We'll see this in action in a minute. So suppose this is your network, yeah, and you've got these nodes. U से आप शुरू करेंगे, and you've got these other nodes, and then ये आपके पास edges हैं, and in edges के corresponding ये आपके पास costs हैं, या distances हैं. Okay. So step 0 में आपने bucket में you've put in yourself U, ठीक है, that's where we're starting from. So U is basically calculating a tree of least costs to all other nodes in the network, ठीक है. Now ये distances हैं to all from U to node V, ठीक है. Distance from U to W, distance from U to X, distance from U to Y, distance from U to Z. ये D और V ये सारे आपके पास आ गए. And दूसरी चीज यहाँ पे ये है कि predecessor node ये है कि वहां तक जाने के लिए what is the node जिसके through, यानी उससे एक पहले predecessor node, what is that particular node. So ये दोनों pieces of information हम देखेंगे, right? So in the first step, U knows that X, W, and V are directly connected at a cost. V की cost क्या है? 7. W की cost क्या है? 3. And X की cost क्या है? 5. And ये जो directly connected नहीं है, तो उनकी cost उसने infinity लिख दी. And to get to there, V, W, and X. The predecessor node, of course, is U. So to get to V, U के through आप जाएंगे, W के लिए U के through, and X के लिए the predecessor node is U. So ये costs आपके पास आ गई, and ये दोनों costs आपके पास infinity है. Okay? Any questions so far? Okay. So basically, each one of these nodes is going to exchange information. कि अच्छा, what is the cost from me to my neighbors? That information gets flooded in the network. So every node floods the information about the cost to its neighbors. That information is flooded in the entire network. So this node will say कि अच्छा जी, ये X and V and W and Z तक जाने के लिए मुझसे ये costs है, और इस information को ये अपने direct neighbors तक पहुंचाएगा. And ये फिर वो information collate करके अपने direct neighbors तक इस information को flood करेगा. And ये इसी information को इस्तेमाल करते हुए अपने tables जो है वो construct करता जाएगा. ठीक है? So basically, information about your neighbors को आप फ्लड कर रहे हैं, सबको बता रहे हैं, एंड जो ये इंफॉर्मेशन यहाँ तक परकुलेट होकर आ रही है, तो ये उससे पूरे नेटवर्क की पिक्चर आहिस्ता आहिस्ता बनाता जाएगा. सो द इंफॉर्मेशन दैट इज एक्सचेंजेस, आप अपने पड़ोसियों की इंफॉर्मेशन सबको बता रहे हैं. दैट्स द बेसिक प्रिंसिपल इन ऑल ऑफ दीज लिंक स्टेट एल्गोरिथम्स. ठीक है? एट द नेक्स्ट हॉप, ठीक है, बेसिकली जब आपके पास डायरेक्ट costs आ गई to your neighbors, you will find out कि अच्छा, what is the least cost to any of my neighbors, and you'll find that the least cost to any of your neighbors is to this node W. So comparing 5, 3 and 7, ठीक है, U के immediate neighbors में सबसे least cost जो है वो W है. So W को आपने उठा के इस bucket में डाल दिया. ठीक है? Because that's the least cost. Now, you can think of this very interestingly as agar ye costs jo hai na, they represented distances. Okay? So let's say this was a string which was 5 centimeters, this was a string which was 3 centimeters, this is a string which is 7 centimeters, and so on. So you have these beads, and I'm connecting each one of these beads with edges which are proportional to the costs. And then I start picking up this particular bead over here. सबसे पहले कौन सा bead उठेगा? It's going to be the one which has the least cost from U, and that's going to be W. So that's the first one that goes into the bucket. So you have resolved W first, because if you think about it, suppose you directly connected ना होता, ठीक है? So वो costs, unless वो cost इससे कम होती, and अगर वो कम होती इससे cost, तो फिर वो जो bead connected था वो पहले उठ जाता. Then that would be the least cost. So whenever you have directly connected nodes, जो उन directly connected node में से सबसे कम cost होगी, हमेशा सबसे पहले वही जो है, that is going to be the first one that's going to be picked up when you pick this bead up. ठीक है? So that's the first one that's going to get resolved. So W is the first node that gets resolved. So least cost to W आपने मालूम कर ली, which is going to be 3. And this is settled. ठीक है? Once this is settled at a cost of 3, उतने में ये हुआ कि इस node ने ये information भेजी अपने neighbors को कि अच्छा, the cost to W over here, and in fact this one knows as well that the cost to V is 3, but that information gets to U in the next iteration, ठीक है? Because ये जो directly connected cost है, ये तो 7 है, but W knows that I can get to V at a cost of 3, and that information is forwarded to U. Then U knows that it can get to V a predecessor node which is W at a cost of 3 plus 3, which is 6. ठीक है. Similarly, while comparing this, ठीक है, अब ये जितनी इंफॉर्मेशन लेट्स से इस तक आ रही है कि अच्छा I can get to X through W at a cost of 7, I can get and so on. None of that is better than this cost 5 over here, so that stays. Now similarly, ये जो cost to Y है, ठीक है, in 2 hops you will know कि अच्छा I can get to Y through W at a cost of 11. I can get to Y through X at a cost of 12. I can get to Y through V at a cost of 11. So भले आप W के थ्रू जाएं या V के थ्रू जाएं to Y, दोनों की cost जो है वो 11 ही है. So if you get two costs to a node at the same cost, 11 ही है, then you can arbitrarily choose कि अच्छा जी आपने W के थ्रू जाना है या V के थ्रू जाना है. दोनों cases में the cost is going to be the same. So you have to come up whenever you have a tie, you can arbitrarily resolve the tie. But for the moment, let's assume that we're going to go to Y through W at a cost of 11. ठीक है. Z अभी दूर है, अभी इसकी one hop next hop में एक hop तक information आ रही है, ठीक है. And for the moment let's assume कि ये अभी हमने infinity रखा है, इसको अभी update नहीं किया, ठीक है. अगर आप कर भी दें तो you would find out कि अच्छा you can get to Z through X at a cost of 14, ठीक है. So you could update that entry that you can get to here through X at a cost of 14. But next row में, next step में, lowest cost once again is going to be 5 over here, and that would mean that you will then resolve node X and place that in the bucket. And once again, if you think about that same analogy, bead one, as I pick this up, सबसे पहले ये W उठेगा, उसके बाद ये X उठेगा. Any questions over here? So next we write down कि okay, to V आपके पास least cost 6 आ गई. Y तक आपके पास least cost is going to be 3 and 8, 11 through W, and through Z आपके पास least cost 14 है through X. Now once again 6, 11 and 14 में least is 6, so this gets resolved. So that means that node V is placed in the bucket. And if you think about this, if you pick up this once again, W पहले उठा at distance 3, फिर X उठा at distance 5, फिर V उठेगा at distance 3 plus 3, which is 6. ठीक है जी. Now to Y through V, I can get at a cost of 10, which is less than this direct cost of 3 plus 8, which is 11. ठीक है. So now Y को जाने के लिए I found a better path. So I can get to Y using a predecessor node, which is V, at a cost of 10. ठीक है. And ये 14 ही है अभी X के लिए. तो इस जगह पे the least cost is going to be 10, and that resolves node Y. You place that in the bucket. ठीक है. So 3 plus 3 plus 4 is 10. And now once again to Z, I can get to Z through Y at a cost of 12, and that's the least. And यहाँ के through it's 14, यहाँ के through it's 13, यहाँ के through it's 13. 12 से बेहतर आपको cost नहीं मिलेगी, so that minimum, once you get all of those multiple paths, is still 12. And in the last step, this goes into the bucket. So U, W, X, V, all of these nodes of the entire network are now resolved, and the least costs that you have to them are as follows कि W तक 3 cost है, X तक 5 cost है, V तक 6 cost है, and Y तक 10 cost है, and Z तक 12 cost है. Now, if you sort of mark these, ठीक है, this is how it becomes. 5, 3, ये path, यहाँ तक 3 plus 3, 6, ये path, 3 plus 3 plus 4, 10, 3 plus 3 plus 4 plus 2 10 is 12. So this is the tree that you have constructed, rooted at U to get to all of the destinations, all of the nodes within the network. So आपको पता है कि okay, if I need to go to X, I will have to go on this path. If I need to go to W, I'll go directly. If I need to go to V, I need to go through W. If I need to go to Y, I'll have to go through V as a predecessor, but to get to there, I need to go through W. So Y के लिए वो packets इधर ही forward करेगा. इसी तरह Z के लिए भी packets वो इधर ही इसी path के ऊपर follow करेगा. So all possible destinations, वो बाद में जब forwarding table construct करेगा, are going to be through X, अगर directly X पे जाना है, and बाकियों के लिए is going to forward them to node W, and उधर से फिर वो route होके destinations तक पहुंचेंगे. Right, so this is an example of a link state algorithm where the cost information to your neighbors is flooded in the entire network, and through that information, step by step, iterative process ke through, each one of the nodes constructs a tree which provides the shortest path to all of your nodes, okay? And that is constructed by tracing predecessor nodes के paths क्या follow करेंगे, and in case of a tie, that tie has to be broken down arbitrarily. Right, so any questions on Dijkstra? Anything unclear here? Very simple. जी.
सर इन स्टेप 1 आपने यू से जो वाई पाथ लिया है वो मुझे एक्सप्लेन कर देंगे दोबारा. 11W जो स्टेप 1 में है.
Step 1 में?
यस सर.
इसमें हुआ ये है कि आपके पास ये पहले केस में तो आपके पास जो डायरेक्टली कनेक्टेड नोड्स हैं उन तक डिस्टेंसेस आपने लिख दिए, प्रीडिसेसर आप खुद ही हैं, यू ही हैं, एंड जो डायरेक्टली कनेक्टेड नहीं है उनको आपने इन्फिनिटी कर दिया. ठीक है. नेक्स्ट स्टेप में ये हुआ कि बिकॉज सारे नोड्स इंफॉर्मेशन ब्रॉडकास्ट कर रहे हैं, अपने नेबर्स तक जितनी भी कॉस्ट है ब्रॉडकास्ट कर रहे हैं. ठीक है. तो अब इसको ये पता चलेगा यू को कि ओके व्हेन दिस वन वी दिस इंफॉर्मेशन गेट्स टू हियर कि ओके डायरेक्टली कनेक्टेड तो कॉस्ट 7 थी, लेकिन जब इसको ये इंफॉर्मेशन मिलेगी कि अच्छा आई कैन गेट टू वी W at a cost of 3 plus 3, which is 6. ठीक है. So it updates that information over here. ठीक है. In the next step, I can get to V through the predecessor node, which is W, at a cost of 3 plus 3, which is 6. Now that cost is less than 7. ठीक है. So therefore, the minimum cost इसने update कर दिया. अच्छा, rather than going directly, I can go to V at a cost of 6 through W. इसने इसको अपडेट कर दिया. ठीक है. इसी तरह से when this information gets here that okay at a cost of 8 plus 3 11 की cost के ऊपर I can get to Y through W. Similarly ये जो information है it's the same. I can get to Y through V at a cost of 11. So both of these costs are exactly the same. Here you have a tie. So when you have a tie, then of course you arbitrarily can choose either. You could have said, Acha, I can get to W through V at a cost of 11. Or you could have said, I can get to Y through W at a cost of 11. तो इसने एक चूज कर लिया because when it is a tie it has to be broken arbitrarily. हमने W ही रखा because ये V से कोई बेहतर बात हमें नहीं मिल रही, cost उतनी ही है, it's equivalent. ठीक है. Now the lowest one of course is 5 to X, and ये आपने X node को उठा के bucket में डाल दिया in the next step. That is the lowest cost. Okay. So in the first step, you only know the direct costs to your neighbors. In the next step, these neighbors are also broadcasting the costs to their neighbors, and वो two hop वाली information आप तक next iteration में पहुंच जाएगी. And that is how you'll find कि okay, I can get to V through W at a cost of 6. I can get to Y through W at a cost of 3 plus 8, which is 11. I can get to Y at a cost of 12 through X. ठीक है, वो टू हॉप वाली इंफॉर्मेशन आ जाएगी. वो यहाँ पे इसमें इसको दो स्टेप्स में जो है ना यानी बट वो थ्रू 12 राइट, बट क्योंकि 12 वो ज्यादा है कंपेयर टू ये 11 वाली पैथ्स के, देयरफॉर हमने उस इंफॉर्मेशन को इग्नोर किया है और 11 वाली ही लिखी है टू के y को जाने के लिए द लीस्ट कॉस्ट इज 11. ठीक है. सो नोटिस के वो इंफॉर्मेशन आपको मल्टीपल पाथ से आ रही है कि अच्छा यू कैन गेट टू हियर थ्रू हियर एट दिस कॉस्ट, यू कैन गेट टू हियर थ्रू हियर एट दिस कॉस्ट, यू कैन गेट थ्रू हियर थ्रू वी एट दिस कॉस्ट. अब उसमें से आपने मिनिमम चूज करनी है, एंड जो मिनिमम है दैट इज व्हाट यू गोइंग टू हैव एट दैट एंट्री. एंड देन जो सबसे मिनिमम है इन दैट एंटायर रो टू ऑल द डेस्टिनेशंस, आप उस पर्टिकुलर नोड को रिजॉल्व कर पाते हैं इन दैट स्टेप, and you put that particular node which is X over here in the bucket. Okay. So if you go back to this, I'll go. So first step में आपने अपने आप को bucket में डाला, जो directly connected nodes हैं उनकी cost आपने note कर दी, बाकियों को आपने infinite कर दिया. ठीक है. Then you want to find one node which is not in the bucket such that the cost to that node is a minimum. ठीक है. And you want to add that to the bucket. So हर step में आप एक मजीद node को bucket में डालते जाएंगे जिसके लिए cost minimum है, and साथ साथ आप update करते जाएंगे the cost to all adjacent nodes to W not in n prime जो कि अभी तक resolve नहीं हुए, by looking at the minimum cost, ठीक है, to an adjacent node, and then from that cost how do you find that जो आपके पास direct information है वहां तक, between that and किसी adjacent node W के through वहां तक what is the cost. So if this adjacent node, new adjacent node के through you find a lower cost to that ultimate node, so you're going to update that, and then next में आप compare करेंगे and जो भी least cost आपके पास होगी वो उठा के आप bucket में डालते जाएंगे. So इसमें for example 5 की, फिर next में 6 की, फिर next में ये 10 की, और आखिर में ये 12 एक ही रह गई है, that will go there, and उसके corresponding जो nodes हैं they will go into the bucket. Right, so any questions here? Any questions? Very simple, and this the bead example is sort of the killer example. Think of them as beads and strings, and the length of the string corresponds to the cost. And जब आप इसको उठाएंगे तो किस order में ये beads उठेंगे, that is exactly how Dijkstra is going to resolve this. Okay? Any questions?
Sir, just another question. Sir, ये जो आपने paths सब resolve कर दिए in red circle, so does this mean that अब मैंने अगर U से Y जाना है, so there always be a cost of 10, and similarly from U to W there will always be a cost of 3, and so on?
Yes, yes, that's the least cost, because देखें basically हो ये रहा है कि after this what you're doing is you are connecting or coming up with this tree, ये जो अभी red marked हो गया, ठीक है. तो इसका मतलब ये है कि अगर अब मुझे X को जाना है तो I will always directly forward packets from U to X, and मेरी cost 5 होगी. और उसकी वजह ये है कि there is no other path in the entire network which can beat this cost. ठीक है,
Right.
इसी तरह अगर मुझे W को जाना है तो I will directly forward packets to W because the cost is 3. There's no other path better than that. अगर मैंने V को जाना है तो I will forward packets to W and W से फिर वो route होके V पे आएंगे. Cost of 3 plus 3 6 पे. And there's no better path than that. I will not use this path over here जिसकी cost 7 है. Because I have a lower cost, I can get to V at a cost of 6 through W. इसी तरह से Y पे जाना है तो मैं पैकेट्स को फॉरवर्ड करूंगा W पे, वहां से वो V पे जाएंगे और फिर Y पे जाएंगे at a cost of 3 plus 3 plus 4, which is 10. ठीक है, I will not forward them to X के थ्रू राउट करूंगा तो मुझे की कॉस्ट पड़ेगी. अगर मैं W and W से Y पे जाऊंगा तो वो कॉस्ट 11 की पड़ेगी. I will use this path, U to W, W to V, V to Y. ठीक है, so जब आपने ये ट्री बना लिया, notice that this tree provides you the costs to all of these nodes in the entire network. So आपने पूरे नेटवर्क के लिए least cost paths निकाल लिए हैं. ठीक है, and paths meaning the यानी entire path, कि आपने इस अल्टीमेट डेस्टिनेशन पे पहुंचने के लिए पूरा जो पाथ लेना है वो पूरा पाथ ट्रेस आउट किया है. ठीक है, एंड फिर इसी से आप फॉरवर्डिंग टेबल बना लेंगे कि अच्छा अगर मुझे एक्स पे जाना है तो आई शुड गो ऑन दिस हॉप, अगर मुझे बाकी सब किसी भी नोड पे जाना है तो आई शुड गो ऑन दिस हॉप. तो फॉरवर्डिंग टेबल में आपके पास बाकी सारे डेस्टिनेशंस के लिए एक ही एंट्री बनेगी कि वो आप W वाला जो लिंक है वो इस्तेमाल करेंगे. अनलेस यू वांट टू गो टू X, उसके लिए ये वाला लिंक इस्तेमाल करेंगे. एंड दैट्स हाउ यू गोइंग टू कम अप विद द फॉरवर्डिंग टेबल, जो कि बाद में बनेगा फ्रॉम दिस राउटिंग टेबल. तो राउटिंग टेबल आपको सारे नोड्स तक की रेजोल्यूशन दे रहा है. इट्स फाइंडिंग द एंटायर पाथ टू द डेस्टिनेशंस. उससे फिर आप फॉरवर्डिंग टेबल बनाएंगे जो कि आपको नेक्स्ट हॉप बता रहा होगा. सो नोटिस कि ये जो राउटिंग एल्गोरिथम्स है, दे प्रोवाइड यू विद द एंटायर सॉल्यूशन, the entire solution with you as the root, and बाकी सारे nodes तक की minimum cost paths आपको निकाल के ये solution दे रहा है. Okay? Any questions? Please ask. This is very important. This is sort of routing. It's a fundamental thing, and it's a very interesting algorithm, which I believe you've covered in your algos course. इस तरह के algorithms. Any question? Yeah, there's a question here. Yeah. So wouldn't it take too long to do this, considering how vast networks are? ठीक है? So it will take long. It's an iterative process. It will take long to actually converge and to get solved. लेकिन वो मसला यही है कि where do we use these? ठीक है? So typically we use them within an autonomous system. So autonomous system is sort of the network controlled by one entity. So one entity would have maybe 20, 30, 40 routers. ठीक है? It's not that you're going to use Dijkstra for the entire world. ऐसा नहीं होगा. ठीक है? So within a region, you'll have ISPs, एक ISP, एक autonomous system में, या multiple ISPs within an AS हो सकते हैं maybe, but typically one AS perhaps to one entity controlling all of that, and उसके अंदर जितने भी 10, 20, 30 routers हैं, उसके लिए आप इसको इस्तेमाल करेंगे for sort of interior routing within that particular autonomous system, and we'll get to that in a while. ठीक है? सो ऐसा नहीं है कि ये ग्लोबल स्केल के ऊपर आप डाइक्स्ट्रा चला रहे होंगे, फिर तो ऑब्वियसली कभी भी इट्स नेवर गोइंग टू गेट रिजॉल्व्ड. सो द स्केल इज गोइंग टू बी मे बी टेंस ऑफ राउटर्स एट मैक्स जिसके ऊपर ये डाइक्स्ट्रा चल रहा होगा. सो इट्स अ वेरी इंटरेस्टिंग, वेरी गुड क्वेश्चन in terms of thinking about how this is going to scale for the entire world. It doesn't practically scale for the entire world. It only is typically used within an autonomous system which is sort of managed by one entity, and वो इसको इस्तेमाल कर रहे होंगे. ठीक है? So a prime example of this, using like ये जो आपके पास link state algorithm है is OSPF, that's open shortest path forwarding का जो है ये protocol, and that is used within an autonomous system. Okay. The book shows another example. I won't go through this, but it's exactly the same way. एक different network के लिए आप इसको solve करते हैं, and with this network that you have over here, what this results in is ultimately this sort of a shortest path tree from U. So U is where you're solving it from. So first step में n prime में आपने U डाला हुआ है. आपके पास जो direct costs हैं to all of them, वो direct cost to V is 2, direct cost to W is 5, direct cost to X is 1, and चूंकि ये Y and Z directly connected नहीं है, so therefore उन तक जो costs हैं, that's infinity. Okay. So Zatash says that, okay. Okay. Yeah. So exactly. So notice that the other thing is that ये जो routing algorithms हैं, they are run in advance because routers exchange this information. They get the routing tree construct कर लेते हैं to all possible destinations, and then उसकी basis के ऊपर वो forwarding tables अपने बनाते हैं. So for example, in the ये जो पिछला example हमने किया है, the forwarding table that they're going to construct in that, if you ये सारा जब कर लिया, ठीक है, अब इसकी बेसिस पे अगर डेस्टिनेशन X है, आप इस इंटरफेस पे फॉरवर्ड करेंगे. अगर बाकी कोई भी डेस्टिनेशन है तो आप इस इंटरफेस पे फॉरवर्ड करेंगे, वो फॉरवर्डिंग टेबल कंस्ट्रक्ट कर लेंगे. So you remember we talked about routing algorithms which are running, routing protocols are running, routers are exchanging information. उससे वो routes calculate कर रहे हैं to all possible destinations. Now they are then going to result in creating your forwarding tables, जो कि आपको बताएंगे कि अच्छा अगर आपका ये ultimate destinations ये हैं, तो next hop आपका क्या होगा? वो forwarding tables वो construct होते हैं. And when a packet actually comes, you do a lookup in the forwarding table, and आपको next hop पे जो local decision, जो immediate decision आपने लेना है कि अगले hop पे कहाँ भेजना है, वो आप कर लेते हैं. So notice that in order to construct that forwarding table, you need to have the complete routing table with you, ठीक है? And वो complete routing table construct करने के लिए you'll be running something like Dijkstra. Okay? ठीक है, so इस केस में once we run Dijkstra, once again ये network है, ये costs हैं, and this is the resulting shortest path tree. So it tells you कि okay, if you want to go from U to V directly आप जाएंगे, बाकी जितने भी node zone तक जाने के लिए U से next hop जो है वो UX ही होगा, ठीक है? That's going to be the next hop, ठीक है? So for all of these destinations, आपके पास अगर V को जाना है, you'll use the next link UV, but for all of the other destinations, you will use the link UX. So this is your forwarding entries that you're going to have as a result of this routing table that you have constructed, जिसमें आप एक shortest path tree बनाते हैं from U as the anchor, as the route to all other destinations that you want to get to. Okay. Now, इसमें you could have if you want to figure out the complexity कितनी है, it's an iterative process. And for each node, you are checking all other nodes, okay? And in terms of the number of comparisons that you're doing, it's going to be order n square, okay? There are more efficient implementations possible, which reduce the complexity of the algorithm, okay? And the other thing that you might want to consider is that you could also have oscillations possible. So for example, अगर आपके पास ये इस तरह की topology है, you've got nodes A, B, C, D, and let us say कि आपके पास यहाँ पे these are sort of nodes which are asymmetric in the sense that the traffic that you have from C to D and D to C वो arrows के साथ show की हुई है. So जरूरी नहीं कि traffic from C to B जो है वो, for example, इस वक्त E है, where the traffic from B to C is zero and so on. So इस case में what you have is asymmetric costs. ठीक है? The cost from A to D is not the cost from D to A. You could have different costs. ठीक है? And suppose कि आपने the cost that you have is equal to the amount of carried traffic. So the greater the traffic that you're carrying, the more the cost. The more the congestion, the more the cost. ठीक है? Now suppose that हर एक node पे C पे जो traffic inject की जा रही है, that is E. B पे traffic inject की जा रही है, that is 1. D पे traffic जो inject की जा रही है, that is D. ठीक है? So C पे जो traffic inject की जा रही है, वो C से B जा रही है. ठीक है? अब ये E traffic और ये 1 traffic, ये 1 plus E traffic is going from B to A. ठीक है? And ये जो 1 traffic inject की जा रही है, D, that is being carried from D to A. So ये आपके पास cost 1 है. So these costs are reflective of the loads that are being carried by these links. So initially आप assume करें कि load 1 traffic is being injected at network at router D, 1 at B, and C के ऊपर E traffic is being injected. ठीक है? And उससे ये distribution है of the loads. ठीक है? And therefore E1 plus E is the traffic being carried from C to B, E है, and from B to A 1 plus E is being carried, and from D to A the traffic that is being carried is 1, and बाकी links पे traffic carry नहीं हो रही, तो therefore उनकी जो cost है that is currently 0. ठीक है? So given these costs, let's say Dijkstra chalta hai, and what it finds is if I go from C to B to A, ये जो path है, because let's say traffic from C to A जा रही है, ठीक है? At the moment it's going counterclockwise, and ये costs है, and it finds out कि अच्छा ये तो if I went from here for this traffic E, I can get at a lower cost because ये सब तो traffic यहाँ पे 0 है, and the cost over here is going to be 0. So if it does that, it's going to shift the traffic, ठीक है? And that traffic will then get shifted to other paths, and that will result in a greater cost on those paths जहाँ पे traffic shift हुई है. And जब दोबारा Dijkstra run होगा, तो then that traffic is going to get shifted back because now वो जो खाली paths हैं उनकी cost कम हो जाएगी, and it's going to decide कि those are least cost paths, lower cost paths, so it's going to shift the traffic back on those paths. So you will get this oscillation कि कभी आप clockwise route कर रहे हैं traffic को, कभी आप counterclockwise traffic को route कर रहे हैं, just based on the fact that if your cost is reflective of the actual carried traffic, तो उसको आप oscillate करते जाएंगे, and that is very much possible. ठीक है? So there's a nice example in the book. If ये book का ही example है, you can see the path will result in oscillation of this traffic, and उसकी वजह ये है कि जब traffic एक path पे carry की जा रही है, उसकी cost है, and जो खाली path है उसकी cost 0 है. When you run Dijkstra, it's going to shift all of that traffic to the 0 path one, and when it does so, फिर जो खाली हो गया उसकी cost 0 हो जाएगी, and then of course when you run Dijkstra again, it's going to shift traffic to that other 0 cost one, and this will result in you'll keep on oscillating between these potential paths. Okay. Okay, so the next thing is distance vector algorithms. Okay, distance vector algorithms, and we'll quickly talk about them. A key example is the Bellman-Ford algorithm, equation that you've seen in dynamic programming. and यहाँ पे if you use a notation, the cost of the least cost path from x to y, ठीक है? So node x से y के लिए least cost path from x to y इसको आप यूं लिख रहे हैं, and ये figure out करने के लिए what you need to do is you need to find out the minimum cost, ठीक है, to a neighbor v, and then the cost from that neighbor v to the destination अगर आप निकाल लेते हैं, ठीक है, so the minimum of that is going to take result in the minimum taken across all neighbors v of x will result in the least cost from x to y. Okay, so notice you want to find out the least cost from x to y. तो आप क्या करते हैं कि you find out a neighbor v of y and you find the cost from x to v, and then the cost from v to y plus the cost from x to v for all different neighbors v of y, उनका जो minimum है, that is the least cost from x to y through neighbor v. Okay, so Bellman-Ford वही network है, ठीक है? So clearly if you find out that okay, the cost from node v to z, ठीक है, from node v to node z is, we'll work this out, is v to z least cost आपके पास यहाँ पे इसने 5 निकाली है. अब कैसे निकाली है? Okay, first of all let's try to identify that. It's going to be this one here and then this one here and then this one here. But how did we find that? Well, to find that आपने, you want to find out, for example, the cost from x to z and the cost from w to z. So the Bellman-Ford equation tells us that in order to achieve the minimum cost, what you need to do is you need to find out the costs to a particular node through all possible neighbors and find out the minimum of that cost. Okay. So let's work this out from u to z. So u to z के लिए you need to find out the minimum cost to an intermediate node v, ठीक है? And then from that intermediate node v, you work out the cost from v to z for all possible neighbors v of z, ठीक है? Now, अब z के क्या neighbors हैं इस वक्त? एक neighbor w है और एक neighbor y है, ठीक है? So if I find out the cost from u to w and add that to the cost from w to z, that will give me one cost from u to z. Okay? So the cost from u to z, एक cost आपके पास आएगी 5 plus 5, which is 10. So the cost from u to z through w is going to be 10. Okay? The cost of u to z through y is going to be the cost from u to y plus the cost from y to z. Now the cost from u to y, ठीक है, ये निकालने के लिए iteratively, if you work out the minimum cost, it's going to be 1 plus 1, because ये बाकी 2 plus 2, 2 plus 3 plus 1, 2 plus 2 plus 3 plus 1, 2 plus 2 plus 1. In subset, lowest cost to y is 1 plus 1, which is 2, which means I can get to z through y at the cost of 2 plus 2, which is 4. Okay? So from u to z, it's going to be a minimum cost from u to V के थ्रू अगर आप जाते हैं, and then V to Z, or U to X, and then from X to Z, or from U to W, and then from W to Z. So the minimum that you're going to get is 4, which is from U to Y, and then from Y to Z. So U to Y minimum cost is 1 plus 1, and Y to Z is 2. So 1 plus 1 plus 2, आपके पास ये minimum cost जो है ना, ये 4 आ जाएगी. So in this, you basically estimate the least costs from X to Y, and you maintain this distance vector, and every node nodes the cost to its neighbor, and you maintain these costs to your neighbors. And the key idea is that each time each node sends its distance vector estimates to its neighbors, and when you receive this distance vector estimate from your neighbors, you update your own distance vector using this equation that, okay, I can get from the distance from X to Y is the minimum distance from X to some intermediate node V, and then from that intermediate node V to Y for each intermediate node Y, which is a set of N. So this is an iterative algorithm. It's for each node. You basically you get this information, and you update this information. And if, for example, you have this very simple network over here, where you've got X, Y, and Z, and these are the associated costs. Okay. From X, the cost to itself is 0. The cost to Y is 2. And the cost to Z is 7. So first step के ऊपर the table, the node table X that you have is this one over here. ठीक है. Y इसी तरह से अपना table बनाती है कि it knows the distance vectors to X as 2. ठीक है. And to Y itself the cost is 0. And to Z the cost is 1. इसी तरह से node Z ने अपना टेबल बनाया हुआ है, ठीक है, from each one of these nodes. So ये जो इसने हर node ने अपने neighbors तक की cost जो उसने estimate की हुई है, this is exchanged, and because of this, then initially node X figures out okay, the least cost to itself is 0. Then the cost to these destinations from each one of these nodes. So for example, the cost to itself through Y is going to be 2. Okay? The cost to Y is going to be 0, and the cost to Z is going to be 1. Okay. Okay, so just one announcement before we proceed, and that announcement is that inshallah you'll be having a short test, inshallah, 15-20 minutes ka on network, on the network layer, ठीक है, and इसके अंदर we'll be covering all the way up to Dijkstra. So link state algorithms that we will have that covered. Okay, so there's a question over here. Isn't U minus W minus Z 5 plus 3? UWZ, एक second. UWZ. इसके लिए कह रहे हैं U. Okay, you understand that. Okay. So we'll cover this, the distance vector one again, but I'll also forward you a couple of links for doing these quick Bellman-Ford test में नहीं आएगा, ठीक है? I'll forward you a couple of a link for working out these aggregations quickly, because that's something that unless you, अगर आपको binary आती भी है और calculator भी है, फिर भी there are some hacks that you can use to actually figure out कि okay, अगर आपने masking करनी है तो how do you do that quickly? So there's a lot of material on the internet based upon that, and I'll probably forward you a couple of good links on that. Okay, so thank you very much.